So we change, as Cam said, we change a little bit of a gear and go into heat and mass transfer in evaporating droplets, right? So droplets, we have all this fancy atomization. So this is the stage that before you go to combustion, this is the stage where things starts to get, lose itself, basically. So it should shrink in size, basically. That's what we mean. Now, heat and mass transfer, why the word mass transfer comes into the picture? It's not just an evaporating process. If the droplet, for example, is binary, okay, then there could be preferential, population of a particular species in the gas phase. For example, if you are dealing with, say, biofuel, right, or biofuel added with ethanol, say, for example. So it's an ethanol diesel droplet, say, for example. So what will happen? What common sense dictates, if you leave a droplet like that hanging, the ethanol will go out first, leaving the diesel behind. The diesel will come a little bit later. So there will be a preferential mixture of ethanol versus diesel in the atmosphere, right? So that can create what we call this concentration inhomogeneity, right? Which will in turn lead to combustion. When we go to combustion, it will lead to combustion instabilities, mixing problems, stuff like that. So to understand this, the evaporation of droplets, so evaporation of droplets requires a little bit of understanding how the transport processes actually take place. Got it? Okay. So this picture that you see, this nice little picture, okay, that is what happens inside the droplet while it is actually evaporating. This comes from our work. Okay. So this is just a picture, but more later. So we start with the typical motivation that, it is there everywhere. Sprays are everywhere. Atomization is everywhere. So therefore, evaporation will be everywhere as well, right? So it is used in, for example, the key feature that most of the people here are most accustomed to is spray combustion, right? Which we will cover a little bit later. Okay, and there is of course the case of spray cooling. Okay, that means you cool a surface. And this is spray drying, which is also going to be covered sometime later in the course. This is not going to be covered, but this is something that we have widely worked on. This is during COVID, the aerosols that comes out of our mouth, that is also a spray that also evaporates, and that's what infects you. So basic mechanism is still the same. What I am trying to harp in over here, it can be a fuel droplet, it can be a milk powder, a milk droplet, it can be a polymeric droplet, or it can be your respiratory fluid. There's a salt and water that is there in your mouth. The basic principle remains the same. It's an evaporation of droplet. Got it? So based on that, we are going to go a little bit deeper. So what is the phenomenology of this? So here is a droplet, and we are not talking about a droplet cloud. This is a singleton droplet. Nice. So what are the processes that you can think can happen? Okay. This droplet exchanges heat and mass with the surroundings, with the ambient. Now the ambient can be of different types. It can be a heated environment, it can be a cooler environment, right? It can be a convecting environment, it can be anything. It can be at any pressure, at any temperature, correct? So if you want to analyze this particular problem over here, okay, and these are the processes that are shown, right? So this, and this is the ambience. Ambience is always subscripted with, infinity, all right? And this S that you see is on the surface. That means surface, but on the vapor side, not on the liquid side, okay? So a complete analysis means that you have to solve a coupled set of equations, right? Okay, in the liquid phase as well as in the gas phase. Okay, so that means you have to solve the Navier-Stokes equation in both phases, right? You have to solve the energy equation in both phases, which is basically the temperature equation. And if there are multiple species involved, you have to solve n-1 species also. Correct? And not only that, you have phase change that are happening at the interface. Remember, this is evaporation. It is a surface phenomena. So phase change happens at the interface, right? So therefore, you need to do something about that, right? And all these equations have to be matched at the interface as well, correct? Liquid phase, gas phase, it has to be matched right there. Fine. And if there is a chemical reaction, which will happen in the case of combustion, okay, combustion never happens in the liquid, it still happens in the gas phase, but it is a little bit removed from the droplet surface. So where the flame will be placed, that is something that we are going to talk about in the next one, that is the droplet combustion, okay? So the types of things that you should consider over here is that how this droplet is moving in the ambient. That means the relative velocity matters. It doesn't matter what is the absolute velocity of the drop or the ambient. It is the relative velocity matters. We saw that the relative velocity was important in atomization. It is also important in the heat and mass transfer considerations, right? These droplets actually are shrinking, right? It's a droplet and it actually shrinks. So it is basically collapsing on itself, correct? If it is collapsing on itself from the, if you are sitting on the droplet surface, what are you supposed to see? You are supposed to see an outflow, right? This is just a coordinate transform, right? It's a reference frame issue. You are sitting on a surface which is collapsing, which is sinking. So you are supposed to see that flow, right? So this is what we call a surface blowing effect, right? That happens, okay? And of course, there is a droplet drag because the droplet is trying to be decelerated in whatever flow field it is in. And because it's a droplet, it's not a solid particle, right? So if there is flow on the other side of the droplet, that means in the gas phase, you are supposed to have a flow inside the droplet also, aren't you not? There has to be. But the flow will be highly attenuated because there is a viscosity trigger over there, right? Because you have to match the shear stress at the interface. So naturally this will slow down, right? But there will be a flow inside the droplet, all right? So we are talking about all these things because all these things are very important when you look at the next stages. So a single droplet, what you think is a nice little thing, right? It exchanges heat and momentum and mass with the surroundings, is actually a set of all these difficulties, all right? So, and there are, you can twist it a little bit. Now the droplet can undergo a deformation and it can evaporate. So it may not be in a spherically symmetric configuration, all right? If there are multiple species, you can see that there are varieties of things that are possible. Also, the droplet can be an oscillating gas flow field, okay? So this is one other aspect that is not touched usually in the literature, because it can be in a vertical field, it can be in a shear field, it can be in a lot of crazy configurations, right? And because they are in crazy configurations, their heat and mass transfer is rather different, right? Rather than a straightforward flow. That means it's not just like a bullet. So don't think of the droplet as like a bullet. It's not a straight arrow. It can go do all these fantastic things, right? So that is a complicated problem, and this is exactly the lower part that you see over here in an oscillating flow field. This has been covered also by us in a recent paper, okay, looking at it from a COVID perspective. All right, so let's understand the transport processes in a little bit more details. So the idea is very simple. The middle one is a droplet and it shrinks. So all you need to first answer the question, how does the radius decreases with time? That's the thing that you are concerned about, right? How the radius shrinks as a function of time. What is that function, correct? Okay, so we can first try to break the problem, okay, and forget about the convective effects for the time being. Let us look at it just from a droplet which is evaporating in a quiescent environment, right? So we bring the concept of quasi-steady, which we'll see what quasi-steady actually means. And the droplet and the corresponding field variables, this T, Y is the mass fraction of the vapor, and C, everything, okay, around the droplet is spherically symmetric, right? Spherically symmetric, okay? This is usually the case, okay? And the ambient pressure is lower than the critical pressure. So you are not having a droplet which is very close to the critical point. So supercritical, all those things are not considered here. And the other part, we will come a little later, what that exactly means. Okay. So how does the evaporation process actually work? And if you think about it, this is what happens. there is a droplet which contains, say, the volatile component is X, right? If it's a water droplet, the entire thing can actually evaporate, right? If it contains some other materials which is non-volatile, that material will still remain inside the droplet, right? Okay, so what happens first, around the droplet over here, you form, if this is a water droplet, for example, easiest to understand, you form a layer of vapor, okay, of water vapor, okay? And then there is an ambient which also has water vapor, right? Like this room. If I place a droplet over here, I'm talking about the space which is near to the droplet. And then by ambient, I mean what is happening there, okay, far away. So what do you think is going to happen? There is a concentration gradient that is created from here to here, right? And because there is a concentration gradient, there will be what we call a Fickian diffusion, right? There is a diffusion of water vapor from near the droplet surface to the ambient. So what happens is that you evaporate, you create this water vapor film. It can be any vapor actually. Ambient is at a much lower concentration. The vapor slowly diffuses away, creates the space so that you can evaporate more. Okay? This principle is very simple to understand. That's why you can dry clothes during the summer when it is not humid. But in Chennai summer, okay, which is humid, it takes a lot of time to dry. Simply because higher relative humidity means that at the far field there is a lot of water vapor. So this concentration gradient is weak. Okay? So basically the gradient is not steep enough. So therefore you are not removing the water vapor in a fast fashion. Right? Simple. So as with any system, any transport system, higher concentration to lower concentration, there is diffusion. And this is molecular diffusion, right? Okay, very good. Here lies the catch, that this droplet region, which is around the droplet surface, so the droplet surface has got a temperature T, okay? That region is saturated with water vapor, which has got a partial pressure, which is same as a saturation pressure at that particular temperature. You understand? So if the droplet temperature is say 60 degrees Celsius, okay, that space will be saturated with water vapor, which is also at 60 degrees Celsius. That is the saturation concentration, right? Ambient can be at whatever, but that can be easily found out because we know the relative humidity. Every day we see the relative humidity, right? So the ambient is the relative humidity. That's why when the relative humidity is like 100%, there is no gradient. So it basically defeats the purpose, right? Okay. So this is what happens. This is the basic mechanism, okay? You don't need to be nervous. This is the same thing as you dry your towel or whatever you do at home. This is the same principle. This is not just droplet, okay? This is anything that you dry has got the same principle over here. Great. So how do you actually find this out? Okay, what you do is a very simple thing. You start with a concentration field around the evaporating water droplet, for example. Well, the equation that you see over there, that has a convective term. Okay, all right. So now what happens is that if there is no air velocity, that term drops out. Okay, now you are left with, therefore, this and this. Okay, you can write it in a 3D sense. You can have the r theta phi component. I'm just talking about the radial direction over here because it is spherically symmetric. That is what you have taken. Okay, all right. And this is the Fick's diffusion law. As you know, D is basically the diffusion coefficient. Water vapor air is well known. If it is ethanol, it can be ethanol air. It can be anything that you can think of. Okay, this D is a material constant. It's a material property, and this is derived, measured, calculated in varieties of ways. We are not going into those kind of things, how you get this information like thermal conductivity, diffusivity, mass diffusivity. Okay, this is a complicated mixture of some quantum mechanics, some measurements, and some theories. All right, but this is known. This is something that is available over there, right? And the water vapor concentration far away is given by the concentration at the surface and the relative humidity. All right. So this is the equation that you ultimately have. Okay, if you neglect the velocity, right? Now, what happens is that comes the question of what I meant by quasi-steady. Did I not mention that there is something called quasi-steady? That means basically the idea is basically you have to drop this somehow. Okay. Otherwise, you can see this equation is no different than an unsteady heat conduction equation, right? So it's an unsteady mass diffusion equation. That's what it is. Okay. Not that this cannot be solved, it can be solved. Okay. So idea is that as the droplet, try to understand this, as the droplet evaporates, the surface regresses. Now, if the evaporation process is very slow, okay, the vapor concentration field can readjust very quickly compared to what the droplet can see. So for the droplet, it does not see any change in the concentration field at all. Understood? If the evaporation rate is extremely fast, that means the droplet is shrinking rather sharply. This is what happens. I think last time we had this question somewhere, that if there is, for example, ballistic heating and stuff like that, right? Okay. Or considering cases which is extremely rarefied flows, okay, these kind of things will not hold. Okay, so here the concept is evaporation is happening much slowly, so the entire thing gets readjusted before the droplet even senses it. As a result of that, you drop this particular term, which is basically makes it a quasi-steady evaporation process. So you are left with a vapor concentration field, which is that. And this is rather easy to solve. As mathematically, it looks exactly the same like a conduction equation. Okay, in one-dimensional conduction equation. That's what it is. All right. You now come to the question, before we move forward, about a concept of wet bulb temperature. Okay. This is also important, particularly when we are dealing with droplets of different fluids, right? Now, what is the normal idea? Let me ask you a question. That say you have a water droplet and you have two ambients. One is say at 500 degrees Celsius. The other one is say at 450 degrees Celsius, right? So what will be your expectation? The water droplet will evaporate faster in the 500 degrees Celsius environment compared to the 450 degrees Celsius environment. Am I right? This makes common sense, right? But what will be the surface temperature of the water droplet in the 450 and 500? Huh? Do you think it will be the same? The first question everybody answered, 500 will evaporate zoop faster than 450, right? But 450 and 500, or rather 400 and 500, whatever you take it, right? Will there be a difference in the surface temperature of water vapor, water molecule, the water droplet, sorry. Okay. The answer is that whenever you heat these droplets, what happens? Initially, there is heat coming. Okay. Where does the heat go? Part of the heat goes towards the sensible enthalpy, increases the temperature, and the part goes towards the evaporation, correct? So there is a budget. This much amount of heat load I am pushing in, and this is what happens. So after some time, this equilibrium is established where the amount of heat that I am putting in goes towards towards the latent heat of evaporation. So the droplet temperature freezes. All right. Okay. And this, of course, depends on what type of fluid you are using. Okay. Standard rule of thumb says what? If the fluid is more volatile, what will happen? And if the droplet is not volatile, what will happen to the wet bulb temperature? This temperature is called the wet bulb temperature, because this is the temperature at which this is obeyed. Where Q dot is the heat that you are supplying, it goes towards the evaporation. Okay. Now the question is very simple. Okay. You understood the question. If I have ethanol versus water, what will happen? Which will have a lower wet bulb temperature? Ethanol will have. Okay, fine. And water will have a higher. And what about diesel? you have to look into the HFG curve, right? You have to look at the latent heat curve and how it varies with different temperature, right? So the system, you don't have to do anything. You create the ambient, the system will come to its own wet bulb temperature. You don't have to do much about that. It will always do that. All right. Okay, excellent. Now that we have this, how to find out, the next question is how to find out that what will be the saturation temperature and the saturation pressure, right? That is what we talked about, because the water, the vapor film that is formed is at the saturation pressure. So this is given by the standard Clausius-Clapeyron equation, right? So you guys all are very familiar with the Clausius-Clapeyron equation, and you can basically calculate what will be the vapor pressure at the wet bulb temperature, okay? This offers quick calc. You can also look it up from your steam tables. If the steam table exists, you can look it up. But when you are writing your code, this becomes rather useful because you can incorporate it in the code. Got it? This is valid only for pure fluids, okay? Clausius-Clapeyron equation, or this form of the equation, is only valid for pure fluids, okay? Because the moment you try to do it with binary liquids or binary fluids, this is not applicable in its current form. There is a version of it which is called the Raoult's law, okay, which is then applicable, which is basically the vapor pressure gets suppressed. It is also very interesting to understand. That means you have the droplet and you have the vapor film that forms at the saturation. That vapor pressure is nothing but the saturation pressure at that temperature, correct? Okay. Now, if you consider Raoult's law, if there is another competitor present with you inside the droplet, what will happen? There is a competition for the same space, correct? There's one space, there is competition. So the vapor pressure is accordingly a little decreased depending on what is the amount of the solvent that is present in the liquid phase at the surface. Okay, so these are the kind of things that you have to account for when you try to calculate this evaporation. Okay, so now that we have set the stage, we know what a wet bulb temperature is. We know that principally when there is no flow, okay, it is all diffusion driven. It's a concentration gradient, and we know that the temperature of the droplet surface is kind of constant, right? And we know that the temperature at the vapor pressure is at the saturation pressure, right? We all of these things we know. Now, depending on whether there is a flow or whether there is not a flow, there are about 6 types of droplet vaporization models that are available. First one is a constant temperature droplet model, essentially what we did right now, right? Then there is something called infinite liquid conductivity model, in which you account for the temperature of the droplet to change with time, but not with space. So the droplet is at the same temperature, but that temperature changes with time. All right. Then there is the spherically symmetric transient droplet heating or conduction limited model, in which you take that there is a temperature gradient within the droplet. Okay. The fourth case is the convective droplet vaporization model. That means there is a convective flow outside the droplet, okay? And somehow, through your conductivity, you are incorporating it into the liquid phase, okay? And the fifth model, which is the most well-known part of the model, is what we call the vortex model of droplet heating, in which you have what we call a Hill spherical vortex that is created within the droplet, okay? And so the idea for doing this is basically you do not solve for the momentum equation within the droplet, okay? So you do everything, it just basically relieves you of some of the burden, right? And the sixth one is a brute force approach. That means you solve the full Navier-Stokes equation, all phases at the interface, and then hope for the best. Hope that your job remains and something good happens at the end of the day. All right, so imagine it is just one droplet. You can manage it for a spray, multi-droplet, where there is interactions between the droplets, okay? Things will get a little messy, okay? So that sets the stage, right? What you can do. All right, so in details, as I said, so there is define a few quantities over here. This is the droplet radius, this is the vapor mass fraction, this is the vapor concentration, and this is the temperature, right? And this is how the function actually varies, okay, from the surface all the way up to infinity. All right, So, what is the mass loss from within the droplet? If you call that m dot over here, okay, so that is the mass loss that is happening, okay, across the surface. And if that mass loss now is converted to a species conservation equation, and then you do this is a simple integral. And if you integrate everything out, okay, there is a little bit of math over it, but this is rudimentary math. You will arrive at something like this, the instantaneous droplet radius. This is how this is given, okay? Here, if you see whatever is there inside is logarithmic, okay? That is actually given by something called BM, a number called BM, which is called the Spalding mass transfer coefficient. Don't read too much into it. It is named after Spalding, okay? He was the one who found it. If you find something, you can name it in your name, but essentially this is the same. This is nothing but the concentration gradient. If you look at it, it's just that, nothing more, nothing less. Okay, and there is a logarithmic term which naturally comes out of this if you solve for this equation, right? So if this is the case, m dot, which is the mass loss, is given by this expression. If you look at this expression very carefully, d is the diffusion coefficient, rs is the droplet surface radius, okay, and it is inside the logarithmic term you have 1 plus bm, where bm is given by this, okay. So bm is nothing but again the differential, okay, again the differential. If bm can go to infinity, technically, if bm goes to infinity, then you actually have a problem, okay. That means when yfs actually is not equal to 1. But anyway, given that these considerations, if you look at this this section very carefully, so as you can see, more is this differential, more is the value of bm, okay. So that part is quite, because more is the value of this, in two ways it can become more. Your y1s can become larger, or once that becomes larger, your numerator becomes large, your denominator becomes small. So therefore your bm rockets up, okay. So actually the curve looks not like a very linear increasing profile with respect to y, okay. So what happens is that this is the expression that you get. So you are very happy. Now you have got an expression of m dot. So if somebody asks you how m dot varies, you say, give me the yfs or y1fs and give me the ambient conditions, give me the d, and give me basically d and then rho is of the droplet, okay. Once you give all these things to me, I can tell you what will be the m dot, right? Very easy, okay. There is of course a catch. Like all things, there is a catch, right? And what is the catch? Can anybody think about it? Okay. We all talked about this mass, right? There is a vapor layer. There is no vapor layer at the infinity, or there's less vapor at infinity. There is a gradient, and that is what drives this whole process. Okay. However, I twist it a little bit and say that this can also, there can be also an energy conservation counterpart to it. What we have looked about is a mass. What about an energy conservation? How the energy conservation will be done? Again, you match it at the surface. Whatever heat is coming, because this is that, okay, that is going towards HFG, right? Okay, that is possible. Okay, so the heat flux at the drop results in the evaporation. This is another way of calculating it, right? Because you have your wet bulb temperature, there is heat coming, and you know that this is a budget. This is also once again a conservation, and it's a valid argument over here, right? So moment you do this, okay, and then you go through the equations, once again very similar to the species equation. Remember, species equation and energy equation are more or less the same. You get one other quantity like this, which suspiciously looks like the mass transfer number, but except this also has the same thing. There is a delta T now. T infinity is the temperature at infinity, or the ambient temperature, aka, and Ts is the temperature at the surface, right? So this is once again, there it was the concentration gradient, here is the heat transfer gradient, right? And this is called Bt, which is basically the Spalding heat transfer coefficient, right? So you get one more expression for m dot. And this time, this expression does not have d. what it should have? It has alpha, which is basically the thermal diffusivity, right? Under which considerations do you think thermal diffusivity and mass diffusivity are the same? So Lewis number equal to 1. Don't you see in combustion there is something called Lewis number equal to 1 fuel and stuff like that? Okay. So idea is, therefore you have a mass conservation, you have an m dot, you have a energy conservation, you have an m dot, right? This m dot has to be equal on both sides, right? Because otherwise you are invalidating one. Okay. In the special case where Lewis number is equal to 1, Bt and Bm are the same. Okay, because these two expressions are exactly the same, except alpha and d, right? So in normal ways, what happens is that if you want to solve this, you normally consider what we call the rate limiting step. That means you have to assume these are twins, right? One is your heat, one is your mass, okay? One cannot run. The slower of the two determines the process. The other one has to adjust. Right? So that is called the rate limiting factor in evaporation, right? So that means you can have a stupendous diffusivity and things it just goes kaput. It is not going to help, okay? You need to have both run in unison, right? So that's why you sometimes validate these two things in a loop. Okay, got it? Okay, but ideally in Lewis number equal to 1, which normally water is not, okay, you normally will have no issues. You can approach it from either side, you will solve the problem. You understood, right? This is understandable. What is a mass transfer limit? What is a heat transfer limit, right? Comes in very handy. And then what you do, then you calculate the Clausius-Clapeyron to calculate the equilibrium between the Ts and Y1s, right? That's what Clausius-Clapeyron does. Because Y1Fs is the same as your vapor pressure, correct? That is the same as your vapor pressure. All right, okay. So once you do all these things, this is the evaporation process in a nutshell. You can do all the math that you want. You can do it better than me. You guys are closer to your IIT JEE pass out year or JEE pass out year or whatever entrance you guys have taken. I'm much removed from that, okay. So now comes the droplet lifetime, because your boss might ask you, give me a number, okay, don't give me all these sermons about, you know, heat, mass and all those things. Give me a number, right? So how long it will take for the droplet to evaporate. So m dot, you can cast it in terms of your d square or r square, right? Because it's a mass, it's a spherically symmetric thing, right? So it is shrinking like that. Okay, and if you equate this to your the two rates, right, and in the case that these two rates are the same, this will now be equal to a constant k, right? If you do the math, just look at the math, okay? This k, in whatever way you casted it, is called an evaporation constant, okay? It is not just a constant, it has got all these terms inside it, which includes the density ratio, Bt and all these other factors. But for a particular setup, it's the same. That's why it's called a constant. So what are the variables over here? You have this, and on the right hand side, you have minus k. So once you do this, now it's a straightforward integration. You will get this expression. Okay. And this is what we call the very famous d square law. Okay. So initially, if you look at it, there will be a region where it will not be valid, and then it will drop. Okay, and this is what the d. So d square is basically, you know, linear with respect to time. Okay, and the slope is constant. Okay, so if you differentiate it, all the slopes are the same, but it does not give you an idea. So for example, kerosene, if you look at it, kerosene and JP4, these are the two fuels. They will differ depending on what is the initial diameter that determines the time. Obviously, okay, it's actually the square of the diameter that is linear with respect to time. Okay, so it is easily understandable. Small droplets evaporates faster than larger droplets, all these things. So this is the d square law, but look carefully. The d square law has got what assumptions? First and foremost, it was quasi steady, then it was spherically symmetric, right? Okay, and then only you get the d square law. So don't apply it everywhere. Okay, that is the sermon. Okay, so this is the droplet lifetime. Good enough? Okay, so we know how to get to the droplet lifetime calculations, okay, in a pedagogical sense, okay. And you can calculate this evaporation constant, either of the two processes you can calculate, okay. So here, if you look at it carefully, if you look at the expression for K, you will see that there are certain peculiarities. Denser liquids evaporate actually slower, and volatile liquids evaporate faster, okay. Got it? Okay, so good. So this kind of concludes this part, that how do you, so you have something like a d square law. You can predict how it will actually evaporate because it depends on that factor K, okay. And the K is a function, as you saw, ambient temperature, surface temperature, the thermal diffusivity, okay, the specific heat, all kinds of quantities that you have access to, right? You know where you are putting your droplet in. You can calculate the wet bulb temperature. You can find out then what will happen, right? Okay. The sensible heat part of the lifetime of the droplet is very, very small. Very quickly it goes to the wet bulb temperature and freezes there. Got it? You can expect it because sensible enthalpy is rather low. It's a very low budget item, right? I can easily put you up in that floor. All right. Great. Now, Lefebvre and others, they did something which is quite interesting. They said that, okay, this is of course when there is no flow, there's nothing. Now, when there is a flow around the droplet, because you are honestly not interested in problems in which the droplet is there in the quiescent environment, right? That problem is good for understanding. That problem is not good from a practical point of view. So what Lefebvre did was that he said, and once again here, all kinds of correlations comes into the picture. So there was a lot of data that was available, okay. Using this data, he assumed that why can't we increase the K, okay, by including a Reynolds number factor on it. Absolutely no physical meaning, okay. It's just a correlation that it works, okay. So what he did essentially was that he updated it using what we call the K effective. That means K effective evaporation, okay. You can also do it in a nicer fashion if we put this inside the K conductivity term. That means the thermal conductivity, okay. So the thermal conductivity is basically jacked up to account for this additional effect, okay, of convection. Sounds very akin to your turbulence models, right? When in your turbulence model, you have the, the nonlinear parts, okay, or basically the parts which you don't have any idea coming out of the statistical moments. You model them, okay, by using an effective diffusivity. It's like using a single quantity for a very large scale kind of phenomena, okay. Ad hoc, but sometimes in certain cases it works. So when you are going to use it, you have to use it with a lot of caution because these do not come from any physical arguments as such. Before this point, it was all physics, right? We had the exact assumptions and we had the exact outcomes, right? Now this is not physics, okay? Remember that. But this is useful, okay? We are not telling that it is useless. It is useful. But you have to know under what range, under what considerations this was actually proposed, like your turbulence models, right? All right, now you go to the 1D convective, droplet vaporization model. That comes next. That when you actually have your convection, what happens? Okay, so what happens when you have convection? This is your velocity scale. This is how your velocity actually changes, right? U infinity is the flow velocity of the surroundings, right? And this is how the velocity is going to decay. So you have a droplet. We already saw that in the secondary atomization, that as the droplet gets entrained, what happens is that the relative velocity starts to decrease with time, okay? That is what it will do. The droplet is gradually going to slow down to the level of the flow, right? So that it is carried by the flow. Larger is the droplet, more is the ambiguity. That's where you heard some numbers called Stokes number comes into the picture, right? Lesser is the Stokes number, faster the droplet comes into equilibrium. Okay. Okay. So, and this is the coefficient of drag. Okay. And these are certain quantities. Okay. And this drag coefficient is also a function of your Reynolds number. Okay. For a 1 hour class, it's almost impossible to say what these things are. Okay. And there is also something called the average gas viscosity. Okay. Which you see over here. This actually comes from a very peculiar notion. Okay. And try to explain it as much as we can. There is a concept now that we are going to develop, which is called the film thickness and the film properties. So as we saw that there is a vapor film that surrounds this particular droplet, right? So what will be the temperature of that vapor film? If I ask you that question, the answer will be kind of, I don't know, it could be anything, right? Surface temperature, which we know is T sat. And then there is a temperature T infinity. Okay. What will be the temperature of this vapor film? Okay. So you can ideally do integration. You can actually find out the length that this boundary layer actually extends to. Okay. And you can do your fancy math and you can come up with some number. That is probably the correct way of doing it. But quick fix way of doing it will be, there's something called an 1/3 law. What it does is that it is a surface temperature, as you can see, and it is 1/3 of the difference in temperature between the surroundings and this. Okay, so it gives more weightage to the surface temperature because that is where it is, right? And it gives less weightage to the temperature differential. Okay, and all the properties are therefore evaluated at that temperature. You understand? So this is the temperature you evaluate. This is called the film temperature. And all these properties, whatever property we talk about the film, okay, that is evaluated at that temperature. Understood? These are all correction factors which makes your results more and more reliable, so to say. Okay. Don't ask that exactly why it is 1/3. Ideally, as I said, you should do an integration of the whole boundary. Like you do your, flat plate boundary layer, like you do your calculation, no? That you extend, this is the delta, and this is how you calculate the whole system. It's a very similar way. You can do it like this. Okay. So now this theory assumes a few things. Okay. So for if the drop was not vaporizing, okay, so there will be a certain boundary layer thickness, right? Certain boundary layer thickness. Okay. And here, of course, your SH, if you have not heard the name, this is the Sherwood number and the Nusselt number. So Sherwood and Nusselt number are basically the same, the brothers of each other in the mass transfer and in the heat transfer. Nusselt number you all know, Sherwood number probably you are not familiar with as of now. Okay. And then there is, of course, the presence of the Stefan flow, which you already said that if you are sitting on the droplet, you see that there is an additional blowing effect. Okay. So that blowing effect will lead to thickening of this boundary layer. Have you heard in your flat plate, in your pedagogic class, I mean, all of you have done masters in some form, right? So if you have a porous plate and you have surface blowing, what happens? The boundary layer thickness gets thickened. Is exactly the same. There's a surface blowing, this thickness actually increases, right? This is exactly what you see over there. Okay. And then there are, of course, these correction factors therefore, because both the temperature as well as the species boundary layer are basically thickened because of the presence of surface blowing. This is called Stefan's flow. Okay. So now, therefore, the droplet vaporization is now given by these quantities. Once again, this is the mass transfer, this is the heat transfer. Okay, the limit, okay, of the two. And by is the same as bm, basically. Okay, just a difference in nomenclature. As you can see, both of these two terms are exactly the same what we did earlier. Okay, and this has got a range of validity, what we stated over here. Forget about all these things. These are varieties of corrections that we apply. Basically, these are the corrections for the surface blowing, which corrects the Sherwood number and the Nusselt number. Okay, 2 corresponds to the case of pure conduction. Okay, which is the case that we already covered. All right. So this is the way that you calculate. Okay, first you are given your TS, U infinity, T infinity, YF infinity. These are all given, correct? So you calculate the corresponding, the mass fractions using the Clausius-Clapeyron equation, okay? Then you calculate the average physical properties of the gas film. Then you calculate the Reynolds number and the Nusselt number and the Sherwood number. Got it? By these expressions. This expression, this is called Rans-Marshall correlation. Again, why am I saying this, that you can get away with a correlation? Because otherwise you need to solve for the entire gas field. Okay, we have not done that. Okay, so a correlation basically makes up for that. All right. Then you calculate the Spaulding mass transfer coefficient, the correction factor, and the modified Sherwood number, and therefore calculate the m dot. Once you calculate, then you do the thermal correction once again. Then you calculate the Nusselt number and the corrected, and you correct for BT and BM, and then ultimately you calculate what is the QL. Got it? All these things you can write in a Fortran code. Okay, I have written it myself. It's not very difficult when you just write it like this. Okay, it's not very difficult. It looks very difficult. It's not. Okay. So now what happens? This is only the gas phase, right? You have done all these nice little calculations. Now what happens? Now there are few things that you should know about the liquid phase. First, one thing that I don't care about the flow in the liquid phase. For me, the liquid phase is spherically symmetric, and then there is transient heating. Okay, that's the first assumption that I have. Okay, got it? So this is the equation of temperature in the liquid phase. Do you recognize that? That's basically a heat conduction equation in the radial direction once again. All right, does not consider the flow within the liquid. So the temperature is basically conduction only. It's conduction driven, right? Only the thing that you need to do over here, you need to have a matching boundary condition now. Okay, the boundary condition sounds a little bit difficult, right? So it is nothing difficult. If you look at it carefully, is the heat coming in and that is conducted inside. Okay, that's all there is. Okay, and then you need, because this is a PDE in 2 dimensions, or basically a second order PDE. So therefore you have a symmetry condition you need to have. So at r equal to 0, the slope basically equals to 0 because it is symmetric, right? So these are the, basically using these 2 things, you can now solve for the temperature field inside the droplet, and outside the droplet you already have this. Gotcha? Okay. And you can solve, and this comes from Chiriniano, Bill Chiriniano's work. Okay, and this is done, for example, D square law. So that is the D square law, and then there is the, forget about the rapid mixing and other types of models. So you can see that the results for many cases looks pretty much the same, but this is the one that is most interesting. This shows the temperature profile within the droplet as a function of time. All right, this is within the droplet. This is within the droplet, and this came out in a long time back, 1993. I think it's Abramson and Chiriniano probably. Okay, now comes the most interesting part, which we are interested in, which we do, okay, as a bread and butter kind of a thing. This is called the vortex model of droplet heating. That means now you incorporate the flow, but here there is also a catch. You don't solve for the flow field, because solving for the flow field means you have to solve for the momentum, then you have to solve for the gas phase. So, and momentum equation is a nasty Navier-Stokes equation. So you don't want to, you want to avoid it at all cost. So what you do is, instead, you assume this flow field. Okay, this is the flow field that is given to you. I have given to you. This is the flow field. You take it, okay, from me. I have told you that this is the flow field going to be. Okay, but of course, the process was not like this. It was not like that Chiriniano and others had a magic wand and they came up with this solution. It's not like that. But you can imagine why the flow field will be like this. Because why there will be 2 vortices? Because you can see one rotates like this, one rotates like this. So at some point of time, there has to be a, a plane of symmetry. So that's why you have a toroid on the top and a toroid at the bottom, right? So that answers kind of this part of the question, right? Why it will be like that. And if there is a flow that is created on the top, that flow has to be closed. Otherwise, you are invalidating your mass conservation. If you just have a flow going like this, then there will be a depletion of mass. So it has to come back. Everything that goes comes back, right? So that is exactly what is happening. So rationally, if you think about this particular flow, it makes sense, correct? There is a symmetry line, and then there is a turning, right? This makes sense? Okay, good. Now, how did he actually solve this? You know how he solved it? He used the Faulkner-Scan group of solutions. So when you actually have a curved surface, you know the Faulkner-Scan? Oh my God. Oh my God. You guys don't know the Faulkner-Scan type of solution? You only know the flat plate? If you curve the flat plate, what will happen? Flat plate doesn't have a pressure gradient, as you know. This kind of a plate has a pressure gradient, starts to develop, right? So what he did was that he took the droplet and made it into small pieces of straight surfaces. So essentially he solved for a polygon. And for each of these faces, you could get the Faulkner-Scan class of solutions. So he pieced them together. All right. Then he developed the flow field. Once you develop the flow field outside, you can develop the flow field inside because there is just the viscosity matching. Okay. So the outside flow field can be 10 meters per second. Inside flow field will be rather small. Understood? Okay. Very good. So that is what was done. Okay, and here you have one more thing which is called the Peckley number. Do you know what a Peckley number is? My God, you guys need they need a crash course on heat transfer. What is a Peckley number? What is a Peckley number? When you say high Peckley number fluid, what does it mean? In for example, if there is a flow through a pipe, okay, we say the Peckley number is much high. What does that mean? In a pipe, so there is heat transfer in the pipe direction in a diffusion sense, right? And then there is a convection speed, right? Okay, so it's like I transfer you the baton, you transfer the baton like that, or I run directly and give the baton there. So I have a high Peckley number system. Okay, so you guys need a crash course on what is Peckley number. Okay, that's period. Okay, so this number comes into the picture because there is convection over here, because there is a flow velocity inside the droplet. What this flow velocity actually does, it gives rise to some interesting things. Okay, so it is not just academic purpose. So now this is the energy equation and the species equation, whatever you call it, that Z can be your T, it can be your species, whatever you can think of. It looks now kind of we are talking, right? So it looks like a tremendously difficult equation to look at it. Okay, but it's not difficult. It has a convective term, which is everything on the left, and then there is the diffusion term, which is everything on the right. Here, of course, you have the uniform temperature. Okay, and now the boundary condition becomes an integral boundary condition because of the flow considerations. Okay, once you have all these things, you have everything within the liquid phase ironed out. Everything outside the droplet is already taken care of, right? All right. This is some of the results. Okay, this comes from Sriparna's work published in JFM in about a year ago. Okay, this shows, for example, look at the temperature field over here, right? If now comes the role of Peckley number, because you saw the flow field was like this. If the conduction and convection, so it's basically the misalignment. So what is conduction trying to do? It's trying to level out everything in the radial direction. So ideally in conduction, you should have this nice concentric circles. High temperature, high temperature, high temperature, right? Something like this, right? Moment you have convection, it is shifted because you saw the flow field. And that is what exactly happens in these nice little pictures over there. Initially, with time, if you allow this to settle, everything will come back to a uniform configuration. But in cases where your droplet is actually traveling fast, say through a combustor, which has got 100 millisecond, 50 millisecond, whatever time scale, your temperature does not equilibrate. Not in this fashion. Okay? So this is temperature. So K or the alpha, thermal diffusivity determines how fast this process is going to lag. Right? But if you are going for the other one, the species, which is the diffusion, right? D, okay? D is traditionally a bit slow to begin with. That means we are dealing with a Lewis number system, which is less than 1, right? In that case, these curvatures will be even more aggravated. So that means if you are dealing with a colloidal system, for example, your droplet has got these small particles inside it, or it has got a solute inside it, right? the precipitation that you are going to do, which actually leaves the baton to the spray drying kind of a literature, your shell, if you look that as your shell is going to be non-uniform.
I don't know this work. It's very recent. And
this is recent. There are other works we did earlier.
This is your work.
This is mine. This is mine. There are other where we actually model this is for respiratory droplets. So this is salt. But essentially the concept is the same, that if you have a solute, which is a non-volatile solute, and that it comes out of the precipitation, what happens is that if the process is too fast, that means it's not very nice and easy process, then you will get this shells, because if you now rotate it.
But I mean, I see the times is 11 seconds, even.
Yeah, this is for respiratory. So, yeah.
So, I mean, it's huge for the application.
Yes. This is for respiratory. But if you are talking about applications like 100 milliseconds, or plasma spray process.
It's interesting to see what is happening until one second.
Correct.
No, I mean,
yes.
At the end, it's not the dimension of the droplet is not changing almost, because
here it will not. Then after that so in cases where the process is very fast, you will get non-uniformity in your solute concentration. That means if you translate now to a spray drying kind of an application, or when you are surface coating an application, your shell structure is going to be non-uniform to begin with. And that all happens because you have taken the flow into consideration. No thermal conductivity model can predict this, because it is not there.
Of course,
it's not there. Yeah, it's uniform to begin with. And there comes the Peckley number, becomes important. If the Peckley number is not important, all these things will be the same as your thermal conductivity model. Understood? Okay, great.